Is it recording? Check. Of course, it's recording. I should share my screen, right? You did not want to come.
What?
You did not want to come today. You did not want to come.
Yes, I thought you will say that don't come.
Me said don't come.
I thought you would say that don't come. It was the last class.
Why would I say don't come? Okay. Guys, I sent you assignment. You saw?
Yeah.
Very easy assignment, right?
Very confusing assignment.
No. Very easy. Like I told you, I said we were going to talk about the assignment today, but I'm not so sure because I don't think we can have time. So most probably you will suffer by doing it on your own. This assignment is easy. Please do a good job because this assignment is going to have majority of the grades. Like a higher proportion of the grades will be in this assignment since it's like a comprehensive term assignment. And even if I might even change my mind and decide to consider only it and forget about every other thing, like so, but I'll put a lot of weight on this assignment for sure. So do a good job. One other thing I'll mention is, I've never mentioned it before. There are 3 or 4 guys, I don't know if guys or ladies, but I can identify their student numbers who have been doing copy work. And the thing I did not realize it. I have realized it, but I deliberately sat quiet because if I tell Nika Hoja, she will just say 0. I deliberately sat quiet because I understand this kind of things. I'm also a student like you, right? And these guys are not even too smart because even though they try to change some things, but they don't change well. And what they do is, like the first person copied from somebody who did this course before. Somebody has done this course before. So it's like we gave similar assignments similar assignments were given in previous semester. So somebody copied from this person and then shared it to the others. And the first person who copied from this person made a mistake because there was a time he submitted twice. He submitted with the old student number of somebody from 2018, and then he realized the mistake and then he resubmitted. These kind of things I always discover. I'm too smart for these kind of things, but I just sit quiet. I will not talk. I don't know who they are, but I can identify their student numbers, and they are looking at me. They know what I'm saying is true. 3 or 4, and they have the same grades in some of the assignments. You see, I'll give them the same grade because everything they did is the same. So the fact that I sat quiet, don't think I did not realize. Maybe you will say that guy is not smart, he cannot realize. I can assure you, I pay attention to every detail. I see everything, but I will just sit quiet. I will be very strict with the marking of this particular assignment. If you copy from previous semesters, I will know. I'll just put it on Turnitin and you'll tell me plagiarism. If you copy between yourselves, I will know because I'm the one marking, right? So, but if you think you can outsmart me, just try, let's see.
But most of the times I open your video and I'm just writing it for you to see, and then that's not copying.
No, that's not copying. You are copying from me. If you copy from me, it's fine. But you don't copy from others. You can copy from me, no problem. But don't copy from others. You understand? Okay. This assignment, we'll talk about it tomorrow. What will happen is that today I will do something. Tomorrow you will have this is the final week of classes. Tomorrow you will have your class with Nigaoja. It's 3 hours class, right? I don't know, maybe she'll use 1 hour or 2 hours, I don't know. Then I'll come in to finish everything. So most probably tomorrow, we'll talk about this assignment, and if there's anything left for me to show you, I will show you. Okay. I should close the assignment now, and we should go straight to what we have to do. I'm going to be fast because there's no time, and I have to finish what I plan to finish. We are talking about assumptions, right? just brief overview as I always do. By the way, guys, these assumptions, we call them classical linear regression model assumptions, correct? We have these assumptions. Like I told you, there are many methods we can use to estimate our model to run a regression. We have ordinary least squares and we have maximum likelihood. We have other methods. But then, according to Gauss and Markov, they have this Gauss-Markov theorem. What they are saying in this theorem is that if these classical linear regression model assumptions are all valid, then the ordinary least squares estimators are the best linear unbiased estimators, right? What do we mean by best? By best, we mean they are efficient. What do we mean by efficient? We simply mean in the class of all linear unbiased estimators, they have a minimum variance. Okay. Of course, you know what linear means. Linear means for all the parameters, like the powers are 1. There is no parameter which has a power more than 1, because if it is 2, it is quadratic. If it is 3, it is cubic. If it is 1, it is linear. Unbiased, you know what unbiased means? Actually, what are we trying to do? We are trying to make inferences about the population, but we cannot have the population. We have just a sample. So the result we'll get from the sample, we'll use it to generalize about the population. So if our parameters are unbiased, it simply means the results we get about the sample, we can use it to make a generalization about the population. But if our results are biased, it means what we'll get from the sample might not be representative of the population. It might be specific just to that sample or something. Okay. So this kind of terms you understand. Now, with the assumptions, there are 10, like 11 assumptions, but some people will say 10. We are not going to talk about all. Okay, Miguel has told you the assumptions, you know them. But now we are focusing on four assumptions, which are multicollinearity, heteroscedasticity, autocorrelation, and normality. These 4 assumptions are very important. Like typically what we do is, maybe in studies, or if you're doing a research and you're doing some things on e-views, we typically test these 4 assumptions. It doesn't mean the other assumptions are not important, but these are like very important assumptions that if these assumptions are fine, then we can assume that classical linear regression model assumptions are working and we can rely on our results. But it doesn't mean that we have just 4 assumptions. Of course, you know there are like 10, 11 assumptions, but we are focusing on these 4. Okay, what I'll tell you is multicollinearity. We did it last week, but I'll still mention it briefly. Multicollinearity assumption is related to regressors. Related to regressors. You know, regressors simply means independent variables, right? These other 3, heteroscedasticity, autocorrelation, and normality, they are all related to the error terms, that is the residuals. Okay. What is the multicollinearity assumption? The multicollinearity assumption is telling us that there should be no strong, that is no powerful linear relationship among any of the regressors. None of the regressors should have a strong or powerful linear relationship, because if any of them has this powerful relationship, then there is multicollinearity. And to test for multicollinearity, of course, we can use correlation metrics. I've showed you. If any of the correlation coefficients is like above 80, you should be suspicious of multicollinearity. We can also use variance inflation factors. As a rule of thumb, we use 10. If you read online or in some books, they will say 5, but we use 10 as a rule of thumb. If all of the variance inflation factors are less than 10, then we can say there is no multicollinearity. But if at least one is more than 10, like 10 and above, then we say there is multicollinearity. Now, if we find multicollinearity, we can try to solve it. First of all, we should identify these problematic variables, that is the variables which have this multicollinearity, and we should see if we can eliminate one of them. But then if you eliminate a variable, you might have solved this problem by creating another problem, which is omitted variable bias. So whenever you eliminate a variable, you should go back and check if you have created omitted variable bias or not. I've showed you. Watch the video. If you don't want to eliminate any of the variables because maybe all of them are useful variables, then you can try to change the proxies. Maybe for a particular variable, you're using this proxy. Try to see if there is a different proxy for this variable. You understand? Or you can try transformation. Of course, it's good to always use log that is lean, because when you take the log, it solves so many of these problems. So you can take log transformation. You can also do ratio transformation. There are many methods I've showed you. It's not like there is a particular method which works for all. You just try. Some will work, some will not work. You might still try everything and nothing works, but just try. Okay, so that is it for multicollinearity. I'm deleting it. Today we are going to look at these three: heteroscedasticity, autocorrelation, normality. These three assumptions relate to residuals. By the way, with normality, we have already seen it when we're looking at descriptive statistics. You can remember descriptive statistics. We looked at Jack-Berra tests, and I said probability value, null hypothesis, data is normally distributed, alternative hypothesis, data is not normally distributed. We saw it, but the thing is that that particular normality which we saw was normality for the data. But this time around, we are interested in normality of the residuals. That's why I'm saying that these three relate to residuals. We are using the same Jack-Berra test, but with the normality we saw under descriptive statistics, it was normality related to the data. Is the data normally distributed or not? This time around, we are interested in if the residuals are normally distributed or not. That's the difference. Normally, most of the times, if the data is normally distributed, then the residuals will be normally distributed. Most of the times, but it's good to test to see. Okay. Heteroscedasticity. What is heteroscedasticity? Yes. So it has to do with variance. Spread is variance, variation. So if the variance of the errors of the residuals is constant, then we say it is homoscedastic. That is homoscedasticity. But if this variance is not constant, that is unequal, then it is heteroscedastic, heteroscedasticity. So the assumption is that the residuals, the variance of the errors is homoscedastic. We don't want heteroscedasticity, because if we have heteroscedasticity, it means we have violated this assumption. What we want is homoscedasticity. Autocorrelation. What is autocorrelation? The autocorrelation assumption is telling us that the residuals should not have any strong linear relationship. That is, the residuals should not be related to each other. You understand? There should be no strong or powerful relationship among the residuals. If we have this kind of powerful relationship among the residuals, then we see there is autocorrelation. If we don't have that relationship, it means there is no autocorrelation. We are going to test all these things. Okay, so how can we do it on eViews? I think, where can I get data? Okay, I have data here. I have data here for one of my studies I'm doing for Cameroon, of course. So we have dependent variables, carbon dioxide. Then we have regressors, GDP, renewable energy, foreign direct investment, and total natural resources. So I think we should go to eViews. eViews is annual data, so I'll put what's the start date. The start date is 1990, and what is my end date? 2019. 1990, 2019. Data. Carbon dioxide emissions. What's the next variable? Is it GDP? GDP, renewable energy. Let's give you GDP, renewable energy consumption. What's the next variable? FDI and total natural resources. So I'll put here FDI, total natural resources. I'll now copy my data from Excel to eViews as usual. You know all these things. Did I share my screen? I forgot.
Yeah, you can.
So everything fine? Okay. You were almost crying. And this, guys, I can assure you, these kind of things will come in your final exam. These assumptions, I can assure you with all certainty. So, I put on eViews my data. Okay, so this is our data. We have carbon dioxide is dependent variable, and then we have 4 independent variables: GDP, renewable energy, FDI, total natural resources. Yes.
Total natural resources is empty.
It's empty?
Yeah, very good question.
Really? What happened? Was I drunk? Oh, I didn't copy it. I see. But thank you. Notice that. It means you're smart, you know.
Thank you.
Is it fine now? Fine. Okay. So, guys, we want to check normality, heteroscedasticity, autocorrelation. First things first, I will write the null hypothesis, because you need to know the hypothesis. If you don't know the hypothesis, then you don't know how to perform the test. For heteroscedasticity, the null hypothesis is that there is no heteroscedasticity. Alternative hypothesis is that there is heteroscedasticity. Autocorrelation, null hypothesis is that there is no autocorrelation. Alternative hypothesis, there is autocorrelation. For normality, null hypothesis is that residuals are normally distributed. Alternative hypothesis is that residuals are not normally distributed. Yes.
And normally we get the null hypothesis or the alternative.
You perform the test with both.
Yeah.
If your probability value is less than, you reject the null and you accept the alternative.
Exactly.
But if your probability value is greater than, then you fail to reject the null and you don't even look at the alternative. So you need to have both.
I mean, which one is good, to have normality or not?
Okay, let me ask you. You as a human being, do you like to be normal or you don't like to be normal?
Sometimes I like to be normal.
Generally, everybody wants to be normal. So we want data which is normal, right?
Okay.
We want normally distributed data. We want normally distributed residuals. For autocorrelation, we don't want autocorrelation. For heteroscedasticity, we don't want heteroscedasticity. We instead want homoscedasticity. For multicollinearity, we don't want multicollinearity. You get the point. Okay, guys, before performing the test, I will tell you something about these assumptions. And the only reason I'm telling you this thing is because I'm a Christian and I want to make things easy for you, else I will allow you to suffer. Just the way I also suffered when I was taking this course. Nobody told me this, but later on I figured it out on my own. In econometrics, you will see null hypothesis or alternative hypothesis almost everywhere. Any test you have to perform, there is null hypothesis, there is alternative. Do you have to cram all these hypotheses? At times you can mix them. For instance, let me just show you something. If you remember, for t-test, we had the null hypothesis, right? I'm wasting time, but it's important. What was the null hypothesis for t-test? Coefficient is equal to 0. That is insignificant, right? And what's the alternative? Coefficient is different from 0. That is significant. Same thing with f-test. The difference is that with t-test, it is for individual coefficients. The f-test, it is all of them at once, joint test. But the same idea with f-test, null hypothesis is that all of them are jointly insignificant, while alternative is that all of them are jointly significant. Okay, why am I telling you this? You don't need to cram this hypothesis. Just put it in your mind that apart from t-tests and f-tests, with all other tests, most of the tests you will see, the null hypothesis is always that there is no problem. And the alternative hypothesis is that there is a problem. Okay. See here, there is no heteroscedasticity, which means no problem. Alternative means there is heteroscedasticity, which means there is a problem. Because we don't want this problem, right? Autocorrelation, there is no autocorrelation, which means there is no problem. Alternative, there is autocorrelation, which means there is a problem. Normality, null hypothesis, they are normally distributed, which means no problem. Alternative, they are not normally distributed, which means problem. So if you have this kind of idea in your mind, you can know this hypothesis for any kind of test. You don't need to cram them, especially for these assumptions. Just know what the problem is and what the solution is. The null hypothesis is that there is no problem, and the alternative is that there is a problem. The only difference is with this t-test, because you see with t-test, the null is instead telling us that there is a problem, because if it is insignificant, it means there is a problem, and if it is significant, it means there is no problem. So apart from t-test and f-test, for most of the other tests, just know that, have that kind of idea. I think it will help you. Okay, that was an aside. Let's go back to what we are doing. So these are our hypotheses for heteroscedasticity, autocorrelation, normality. First, we are going to start with autocorrelation, because I already told you something about it. Guys, before you perform these tests, you must run the regression. So on eViews, I want to run a regression. I should go to quick, estimate. What's my dependent variable? CO2. Then I have constant, GDP, REC, FDI, TNRO. That is our regression. Now, to perform autocorrelation tests, we are going to use two tests. It's always good to use more than one test for these things, because if both of them give you the same results, then we can say your results are robust, right? So actually, I mentioned it to you before that we can use Debye-Watson statistic to test for autocorrelation. I mentioned it, right? So check this Debye-Watson statistic. If this statistic ranges between 0 and 4, that's the first thing I'll tell you. If it is around 2, if it is 2 or around 2, it means there is no autocorrelation. But if it is far from 2, that is, it is closer to 0 or closer to 4, it means there is autocorrelation. That's the first test. Okay. I searched it from the internet just so I can be sure and show you. And I have it here. Debye-Watson ranges from 0 to 4. If it is closer to 2, it means there is no autocorrelation. If it is closer to 0, that is far from 2, it means we have positive autocorrelation. If it is far from 2, that like closer to 4, it means we have negative autocorrelation. So that is the first test. Okay. But guys, there is a problem with this Debye-Watson statistic, which I will show you again. By the way, there is a document I prepared personally. I sent it to some of you. As I can remember, I prepared this document myself, like many semesters ago. And this document is focused on multicollinearity, heteroscedasticity, autocorrelation. Like, it gives a lot of details about these 3 assumptions. This document is important for those. Anyway, I'll talk about it later if I have time. Where's autocorrelation? Guys, actually, I have so many things to tell you, like 1 million things to tell you, but I cannot find time to tell you. So at times I get confused, you know. So with autocorrelation, so you see, we can use Debye-Watson test to test for autocorrelation. But as a criticism, this Debye-Watson test checks autocorrelation only at lag 1, like 1 lag. If you go to lag 2, lag 3, lag 4, whatever, you cannot use this test. So because of this, we have a more general test, which is known as Lagrange, anyway, let me not, BG test. It's an LM test, like Lagrange multiplier, but we'll call it BG test, Bush-Godfrey test. So we in addition to using Debye-Watson test, we should also use this BG test. It is the more general test for autocorrelation. So on eViews, how do we do this BG test? Now, after we have estimated our regression and we have this page of the regression results, you must be on this page. If you are not on this page, you cannot do it. On this page of the regression results, go to View, come to Residual Diagnostics. Remember, I told you these assumptions are related to the residuals. So come to Residual Diagnostics, and here you see serial correlation LM test. Guys, technically, autocorrelation and serial correlation are not the same, but at this level, just take it to be the same. So this serial correlation LM test, that is Lagrange multiplier test, is actually the BG test. Now you can suggest a number of lags. Remember, I told you with Debye-Watson test, it tests only at lag 1. But you see, with this BG test, you can use lag 2, lag 3, you can change these lags. But whatever eViews suggest to you, allow it like that for now, don't change it. Press OK, and you have your results. This is our results. So you see, it is called BG test, Bush-Godfrey test. It's actually an LM test. Now, how do we interpret the results? Forget about all these too many numbers you're seeing here. Focus just on this. Just on this. Just on the F statistic and this probability value. Only this probability value is of interest to us. You see this probability value, it is 0.2. That is 20%. So it means it is higher than 5%, right? Which means we cannot reject the null. Therefore, there is no autocorrelation. If it was less than 5%, we would have rejected the null and we would have accepted the alternative, which says there is autocorrelation. Very easy test. Okay, just as we did with multicollinearity, we tested it using correlation metrics and variance inflation factors. And we said if there is multicollinearity, then we should look for a way to solve it, right? Similar thing with autocorrelation. Okay, fine, our test has told us that there is no autocorrelation. But assume that we found autocorrelation. How can we solve it? Now, to solve first thing I'll tell you is that log transformation solves many of these problems. So it's always good to use logs. Always use log because it solves many of these problems. So log transformation can be one of the solutions. But then we have another solution, which is known as Newey-West methods. I will show you. Before showing you, I should show you the document. So you have autocorrelation here. Solutions to autocorrelation. Theoretically, if we know the nature of the autocorrelation, then we can solve it using this method, GLS. They call it generalized least squares. But in practice, we don't use it. Why? Because if there is autocorrelation, we don't know its nature. So we cannot use this method. We can only use this method if we know the nature of the autocorrelation. But that's just theoretically. So since we cannot know the nature of the autocorrelation, we should use a different method, which is known as Newey-West method. This Newey-West method, they also call it heteroscedasticity and autocorrelation consistent errors. It's on eViews. So on eViews, what you should do is, assuming we have found autocorrelation and we want to solve it, so we should re-estimate the model, but we are going to use that Newey-West method. So just come here to estimate. You see everything is the same. Come here to options. Instead of ordinary, change it to Newey-West. Everything fine. Estimate. So you re-estimate the model, but you are using that Newey-West method. After we have used this method might, it is not a guarantee that it will, it might correct the autocorrelation. Therefore, after estimating it, we should go back and still perform the tests to check if it has corrected it. You understand? So still come again to view, come back to residual diagnostics, and then still perform the tests. Sorry, this is heteroscedasticity. Still perform the tests, serial correlation. Don't change the lags for now. And then, so I'm just initially we did not find autocorrelation, but I'm just telling you that in case you find autocorrelation and you want to solve it, if you take logs and it does not work, try Newey-West method. It might work, but it is not a must. It is not a guarantee that it will work. It might work. Okay, so that is it for heteroscedasticity. Sorry, autocorrelation. You know, I get confused at times, so it's normal. So I will delete autocorrelation. So guys, if you notice, I'm coming. If you notice what I'm telling you, for each assumption, I tell you how we can test for it, and I also tell you how we can solve it in case we find it, right? And as I'm telling you, in this document I prepared, I have a reason for laughing, don't bother. What I did was, for each of these assumptions, I have discussed the nature of the problem, the cause of the problem, what causes this problem, what is the consequence of using ordinary least squares if we have this problem, because you know, according to Gauss-Markov theorem and classical linear regression model, we should only use ordinary least squares if all these assumptions are valid. So if one of them is not valid, we should not use ordinary least squares. But then some people might try to use ordinary least squares even if they have this problem. So what will happen? There is a consequence for using ordinary least squares with this problem. So I've also talked about these consequences, and I've also explained how to test for each of them and solution. You understand? So that is it for autocorrelation. Now, heteroscedasticity. How can we test for heteroscedasticity? Okay. Guys, on E-views, we have 5 tests. We have white test, glass jar. Anyway, I should show you. By the way, you have the hypothesis for heteroscedasticity, right? Okay. On E-views, estimate, I should change it first back to ordinary because I'm done with autocorrelation. I want to. So this is my model. Estimate, this is the model. To do this test, you must estimate your model. On this page of your results, go again to view, residual diagnostics, heteroscedasticity. Now we have 5 tests on E-views. We have the Bush-Pagan-Godfrey test, we have the Harvey test, Glaser test, Ash test, and White test. What I'll tell you is, white, for me, if you ask me, white test is the best test. It's the most general test because most of these tests have their criticisms, but white test is the most general test. Just you remember, like with autocorrelation, the Watson test has this criticism, and we have the Bush-Godfrey test, which is the general test, that perform both of them. With heteroscedasticity, we have these 5 tests. When performing these tests, please do 4 of them, don't do ASH. This ASH simply means autoregressive conditional heteroscedasticity. This test works well with high frequency data, like daily data, weekly data, monthly data. But since for this course we are using just annual data, this test is not too important because there is no volatility. You know, you can have volatility with high frequency data. So forget about this ASH test for now. Do these 4: Bush, Pagan-Godfrey, Harvey, Glaser, and White. Then compare the results. Some of the tests might tell you that there is no heteroscedasticity. Some of them might tell you that there is heteroscedasticity. Go with the majority. So like there are 4 tests. If 3 says there is heteroscedasticity and 1 says there is no heteroscedasticity, then we conclude that there is heteroscedasticity. If 2 of them say opposite things, like 2 say there is no problem and 2 say there is problem, then trust the one which comes from white, because white is like the general test, you understand? But it's good to perform all the tests and like compare the results in the table before you make your decision. Okay, let's start with white tests. So we have white tests. Just press OK. Actually, we should not include, guys, I'll show you something. We should not include cross terms. White tests, don't include cross terms. You can include it, but don't include it because it will confuse you. So for now, don't include it. Perform the test. You have the results. And again, check just this line, right? You see this, it is greater than 5%. So we are not able to reject a null. Therefore, there is no heteroscedasticity. The same thing. So that's it for white test. Let's check the others. Let's check Bush, Pagan, Godfrey. Again, we cannot reject, no heteroscedasticity. Let's check the next. Harvey test. Again, we cannot reject. We'll check again. Glaser test. Again, we cannot reject. So all tests are telling us that there is no heteroscedasticity. So we conclude that there is no heteroscedasticity. But if maybe some say there is hetero and some say there is no hetero, then go with the majority. You get the whole idea. So in this data, we have found no heteroscedasticity. But then, what if we find heteroscedasticity? Because in some data you will find heteroscedasticity. We have to look for a solution. So how can we solve it? Again, log transformation can help, but assuming that it does not help, then there is a method which is known as Huber-White robust standard errors. I'll show you in my document, heteroscedasticity solution. So if we are to solve this, we should use White's heteroscedasticity consistent standard error. They also call it robust standard errors. On EViews, you'll see the Huber-White. That's the method we use to correct heteroscedasticity. Okay. So guys, this method was proposed by somebody called White. And you remember, to perform heteroscedasticity test, one of the tests is White test. That test was created by him. And if we find heteroscedasticity and we want to solve it, we use this Huber-White method, which was also created by White. So this guy, Robert White, he has these two important contributions in econometrics. First, he proposed a test to test if there's heteroscedasticity. And then secondly, he proposed a solution in case we find heteroscedasticity. Okay, so let's go to EViews. By the way, guys, we have 2 more minutes, but we have 7 more minutes. Who has understood? Everybody understood, right? We have 2 more minutes, then we have 7 more minutes. Okay. If you do not understand, then I think there is a problem with you. So back to EViews. Okay, we have found that there is no heteroscedasticity. But then what if there is heteroscedasticity and we want to correct it using this Huber-White method, which they also call robust standard errors? Same thing, estimate, come to options, and here change it to Huber-White. And then re-estimate. If you re-estimate, it might solve this heteroscedasticity. It is not a guarantee, but it might help. That is why, if you estimate it using Huber-White, you should go back, test again for heteroscedasticity to see if you have solved this problem. You understand? So that is it. By the way, guys, are you understanding these kind of things? I feel like I'm just singing a song here. Is it interesting? Good, right? Okay. So that is how we can test for heteroscedasticity. And that is how we can solve it. Okay. Normality. Same thing. So I should re-estimate my model. I should change it back to ordinary. Re-estimate my model. I have my model. In order to perform this test, you must estimate your model. Come to view, come to residual diagnostics, come to normality test. Have you seen? You have the histogram. Now, if you check down here, you see Jack Berer and you see probability value, right? If you look down here, first of all, just by looking at this graph, it gives you an idea if it is normally distributed or not. You know the normal distribution, it gives you an idea. But to formally perform the test, we should do a statistical test. So check this probability value down here. It is 0.02. 0.02 means 2%. It is less than 5%, which means we should reject the null and accept the alternative. So it is not normally distributed. You understand? Now, since there is no normality, that is, it is not normally distributed, how can we solve it? This is a very difficult question because it is difficult to solve non-normality. Of course, log transformation can help. Let's say, like you see, our data, we are using raw data, we do not use log. Maybe if we take the log, it might become normally distributed. But the best way to solve normality is increase the sample size. Maybe in your sample, you have just 30 observations. Try to have 100 observations. The more observations you have, the more normality becomes plausible because of central limit theorem. I don't know, you have an idea about central limit theorem. Try to read about it. Central limit theorem. I don't know. Central limit theorem. Central limit theorem states that if you have a population with mean lab, guys, I don't want to waste time, but read about it. You can read about it. So because of central limit theorem, if the more sample you have, the higher the probability that you will have normally distributed data and residuals. So the best way to solve non-normality is to increase sample size. So that is it. I've not said you should go. I've said that is it. But you wanted to go. We have 3 more minutes. So I've showed you autocorrelation, heteroscedasticity, normality. Previously, I showed you multicollinearity. And I also told you that if you remove a variable because you want to solve multicollinearity, then you should check omitted variable bias. So basically, I can say we have done the assumptions. And what I'll show you tomorrow, let me just give you an idea. In addition to other things, I'll show you maybe some stability diagnostics. Oh my God, can I find time? You want to ask the question?
No, just showing one note.
Yes, I'm listening.
Tomorrow you should simplify the assignment.
Why?
Because
Well, I'm saying trying to make it more difficult for you. We are saying I should simplify. Okay, guys, if you estimate your model and you come to view, you see we have seen residual diagnostics. We can also check stability diagnostics. Under stability, we'll check Ramsey reset test. We'll try to see if there is any misspecification error or not. Whatever, I will show you tomorrow. Since some of you want to go, I should let you go.
Well, I have a question. For the autocorrelation, we check the serial correlation LM test.
By the way, I should stop recording first before you ask me. Yes, I'm listening.
Yeah, and I was asking for the autocorrelation. We should to find if we have autocorrelation or not. We should like go to serial correlation.
Yes, serial correlation and autocorrelation, we can say they are the same. So for autocorrelation, use Debye-Watson test, use that LM test, Bush-Godfrey, both of them. For multicollinearity, use correlation matrix, use variance inflation factor. For heteroscedasticity, there are 5 tests. There's white test, Glaser test, and all the rest. And for normality, we have the histogram, that is the Jack-Berra test. Okay, I think that is it. Tomorrow, I will finalize everything when Nigauja is done. Then we can talk about the assignment. And if I find time, I can also show you how to collect data from the lab using the data stream, because I know some of you are doing thesis next semester, so maybe you will need it, but it's just extra. It's not like I'm supposed to show you. If I have time, I will. Okay.
Hear about the midterm, you're not yet.
Your midterms, I don't know, but as I was saying, most probably
Tomorrow we'll talk about this.
we'll talk about it tomorrow. Did I stop recording?